So today we're going to learn about convolution operation, and we have learned about convolution in the previous semesters, maybe in terms of analog perspective. Now, if I am to define convolution, what it is, I can basically call it as a mathematical operation that is performed on two signals, x of k and h of k, which will create a resultant signal y of n. And it involves the following operation between the signal components. One, it involves addition of the components. It involves multiplication. It involves folding and shifting of the signal components of one of the signals. So with these four operations running in the background, the convolution tends to become a complex operation. Now, where does the relevance of convolution come in? For our understanding, we can treat a signal existing in physical domain to be a convolved one. For example, the speech that you hear from my end, it can be treated as a convolved signal of so many components happening over here. See, you need to understand the fact that you are hearing my speech, or you are making sense out of the speech that is coming out of my mouth, and it is because of the fact that whatever you hear is basically a process that is involved with the air transmission or the airflow in my windpipe and all those kind of things. So there are so many things that are coming into picture over here. One is the air movement through my track over here, and then there is a movement of the throat muscles, and all those kind of things make up the sound, and all these things work differently in each one of us, which is why our voices tend to be different in the way that we hear, and it is the reason why it is treated as a convolved signal. Now, that is a part of an audio signal processing concept that you would be learning later, but please do understand that every signal existing in the physical domain can be treated as a convolved one. Now, again, why transforms are important in terms of a convolved signal? You might have heard of a property of a convolution that convolution in time domain is equivalent to multiplication in frequency domain. And with convolution becoming a complex operation in time domain, the same signal can be easily processed in the frequency domain, because convolution is equivalent to multiplication in frequency domain. So again, if for easier processing of the signal, it is important that we transfer it to frequency domain, and that is where the importance of transforms come in. And I hope these concepts are clear. We'll be focusing more on convolution and the two types of convolution, basically linear and circular convolution. Convolution for a discrete system can be given by this particular formula that you see over here. Y of n is equal to summation k equal to minus infinity to infinity x of k into h of n minus k, where x of k is the input signal, h of k is the impulse response, and y of n is the output signal. Now, if these three signals, as you know, are existing in the formula, y of n exists over here and h of k is existing over here, then what must be h of n minus k? So we have a signal like h of k, and what is the relation between h of k and h of n minus k? So when we look at this, we can consider some processes happening in between. Now, h of k, if it is folded, it becomes h of minus k. And when I speak about folding, I am talking about folding at the center point, that is 0. So if h of k is folded, we get the signal as h of minus k. And if this signal is shifted, that is h of minus k plus n. Now, if n is a shift that comes in, it becomes h of, this becomes a resultant of the shifting operation. So this can be treated as equivalent to h of n minus k. Now, that is what happens here. So you have a signal h of k that is available here. Now, this component h of n minus k basically refers to the fact that h of k is first folded, which gives you h of minus k, and when h of minus k is shifted on this basis of factor n, it becomes a shifted and folded version. So that complies these two concepts that I have mentioned, the operations that I have mentioned here, folding and shifting of the signal components. So now we are going to perform a question of this linear convolution between two signals x of k and h of k to form a resultant signal y of n. And now x of k here is given as 1, 2, 3, 4, and h of k is given as 1, 5, minus 7. Now, before moving ahead into the actual problem, we need to have an understanding about few concepts. One, we need to find out the length of the output signal. So when we speak about the length of the output signal, which is y of n, it can be treated as L1 plus L2 minus 1. So L1 basically refers to the length of signal x of k length, and L2 basically refers to h of k length. So as you know, there are four components here. So L1 is 4 and L2 is basically 3 minus 1. It will have a resultant length of 6 components. So that will be the length of the output signal y of n. It will have 6 components. Now the next point that we have to know is the starting point of the output signal. I call it the starting point of output signal, or basically from where the signal will be starting. What will be the position of the signal, that where it will be starting. So for that I need to know the starting point of S point. I basically refer to starting point of x of k and starting point of h of k. So for that what we need to do is, since our signal basically is given in this format, by default it can be taken to be starting as starting point as 0. That means the signal will be starting at the point 0, where k position will be 0 and the k position of this signal is also 0. So both the signals will be starting from 0. So the starting point of the output signal will be 0 plus 0, starting point of x of k plus starting point of h of k, which will be 0. So basically what we can infer is that your y of n will be containing 6 components: 1, 2, 3, 4, 5 and 6, which means they will be y of 0, y of 1, y of 2, y of 3, y of 4 and y of 5. So there will be 6 components primarily in this output, which will be designated as y of 0, y of 1, y of 2, y of 3, y of 4 and y of 5. Now we need to have an understanding about this particular signal, and basically the signal can be represented in another manner. I am treating it as a separate example, not this particular question. So if x of k was represented as 1, 2, 3, 4 and with an arrow under 3, you have an arrow under 3, it would basically mean that this particular position of 3 is beginning at 0. So then this signal will be starting from minus 2. If this is 0, this will be 1 and this will be minus 1 and this will be minus 2. So the starting point of the signal will be minus 2, and hence this would have been minus 2 plus 0, where the starting point of the signal will be minus 2, which means again there would have been 6 components starting from y of minus 2, y of minus 1, y of 0, y of 1, y of 2 and y of 3. Again there will be 6 components, but it will be starting at y of minus 2, y of minus 1, y of 0, y of 1, 2 as well as 3. So that has to be kept in mind. Okay, fine. Moving on, we have seen an example of a linear convolution, and I had mentioned an example where x of k, it could be 1, 2, 3, 4 and h of k can be 1, 5, 7, and x of k could be 1, 2, 3, 4, where arrow is under 3, and which means the position is 0 and this becomes minus 2 and this becomes 1, 5, 7. So this remains 1, 5, 7. So basically my point here is that linear convolution can be used for aperiodic as well as periodic signals which are of different lengths. lengths. In comparison, your circular convolution, which we'll be learning about in detail, it cannot process signals that are of this nature. By that I mean there are two conditions to be checked in circular convolution. One, the periodic signals should contain 0 to n minus 1 samples, both the signals. I mean, if the signal length is n, it should be the same for both the signals. That's the second point. The length of the signals must be same. And if it is 5, okay, both the signals should have 5 components. And if it is 4, both the signals must have 4 components. And the length of the sequences must be from 0 to n minus 1. So when we compare it with this particular signal over here, we cannot definitely use it for the signal that is shown over here, and primarily because of the fact that by default this signal's starting point is 0, so that is fine, but here the lengths are different. So since the lengths are different, they must be made equal to the same length, and x of k, if it is 1 2 3 4, the length of h of k, since it is 3, it must be adjusted to make it to the length of this many number of components. So there are only 3 components here and there are 4 components here. So S0 can be added to make it of the same length. Now this process is known as zero padding. The process of adding 0 additionally to make the signals of the same length. This process is called zero padding. So I hope that concepts are clear. And that was a basic introduction to convolution, and we'll start off with the linear and circular convolution in the next video.